So, hello, welcome everybody to my talk, and I will start immediately with a small fact. Did you know that about 50% of scientific papers which has been submitted last year to the ArchiveX, which is a portal where scientists are submitting their papers for peer review from the area mathematics, physics, and computer science, were from area of machine learning. Machine learning is gaining a lot of attention. In the year 2016, AlphaGo has managed, just after only a few hours, to playing against itself to beat the human, and showed us that the 2,700 years of human history of playing Go led us only to the local minimum. AlphaGo was powered by machine learning algorithm. One of them was reinforcement learning. But mostly, they are neural networks which are powering the systems. And we will have a look on these systems in this talk. And we will start with a tweet. This tweet states that gradient descent can write code better than you. I am sorry. Usually, we can ignore tweets, random statements on the internet. Even this one is really strong. Somebody is telling you that I can write a better code as you do. And gradient descent is algorithm behind machine learning. But what we cannot ignore is author of this tweet. It's Andrej Karpathy. For those of you who heard this name for the first time, he's kind of Jake Wharton in the machine learning community. He is director of artificial intelligence and computer vision at Tesla. And in time when he's not fixing Tesla's self-driving cars, he's writing really great blog posts and writing very nice open source software. And he has also a very great history in machine learning and learning, and general in learning. These tweets is kind of introduction in the new era, which we call sometimes software to zero. What does it mean, software to zero? To understand this, we will have to look the first how we are writing code now, or what we did before software to zero. So in traditional approach, you write your code, and as a code, you define the rules. This code is compiled to the application, and with given data, you are getting the results. So you, as a human, you are defining in source code your rules, and executing the program, you are getting the results. Machine learning flipped this approach. It takes expected results. It takes data we usually have, and it needs a lot of this data, and tries to figure out rules. So the output is the rules, and the work which leads to these results is a training. So the main difference is who is responsible for what. This approach may sound like strange for the first time, but there are some use cases very useful. For example, if humans are not having hard job to find out the rules. Sometimes it's really hard to write good rules as a code. Another example is if your system and system behavior is changing in the time. As a very good example, we read very often about this, and I will agree on that, is the spam filter. So, of course, as a programmer, as a code writer, you can write your regex samples and so on, and it will work quite well. We are doing quite well for a long time with this traditional approach. But we also have a really hard time with the new creative way how the spammers are going to cheat on us and so on. And I can assure you, you are not getting the double coins back if you are sending Bitcoin to the Elon Musk. There are also another examples where machine learning works quite well. The one on this computer vision, we know from the videos, from pictures from Tesla, it works quite well. I would also mention application from medicine, where meanwhile our specialized system to recognizing illnesses even having a better performance as the best human experts in the category has. With the difference, they work 24/7, they are not having unions, they are not getting vacancies, and so on. Another quite good example is speech recognition and synthesis. I guess everybody knows it from your assistant or your mobile phone or from your smart assistant at home. Machine translation is also another thing which works really well in this situation. And recommendation systems are always mentioned as a good example, and they are very often used as machine learning system. And for me, the one we probably all know is not really working really well because they try to suggest you have to buy another shoe if you already bought a shoe, or you have to buy another refrigerator if you already have one. For me, it's a proof that these systems are evolving, and maybe it's good, maybe you can get sleep and that systems are not taking over us. Also very useful is our use case with natural language processing, where machine learning-based system can very effectively analyze a lot of text, provide insights, provide sentiment analysis, and intent recognition. In financial sector, sometimes our system uses not very transparently. Sometimes is machine learning system deciding if you are getting loan or not. So we have machine learning, we have neural networks, we know how this works, and I would like to challenge if this machine learning system can write better software as a human can do. As an example, I took the case from the rocket science, especially from the Apollo 11 mission. And I don't know if you can read this really well, but this is source code taken from GitHub repository, which is a rewrite of all source code, everything available on the Apollo mission. And this is implementation of a sign function. Also, I have to mention Margaret Hamilton. I am in the wrong room apparently now, which was the director of software development in MIT lab, which was responsible for this Apollo 11 program. And in some sources, I had even found that she is the author of the code. But I didn't really find the link. But to stay in the spirit of this conference, I wanted to mention her too. So let's have a look on the sign function. I guess everybody remember this. It's having 0 in 0 and 1 in p divided by 2. It's periodic, quite simple. So nothing to deal with. The fact is that Apollo 11 computer was not so powerful as your mobile phones today are. It has only, if I get remembered, only 2 kilobytes of RAM and about 7,000 kilobytes of memory. So the constraints of compute power and memory was really strict. So the scientists, the developers, at the time, they use a trick, and instead of providing the implementation of sign function, as we do it usually with full implementation with tables and coded by Taylor series, they decided to use approximation. You can see on this plot, you can see 2 curves, and the orange one or yellowish one is the approximation they used to calculate. As you can see on the upper side, this is the simple polynomial, so it means to calculate the sign function, you don't need huge tables, you don't need huge series to calculate. These are only a few multiplications and summations. So this was important to have this calculation efficient. But as you can also see, starting from approximately 1.5, the value is starting to diverge. So we are having this error. But this is fine, because the developers, they find out that for navigation, and it was a crucial part of Apollo mission to get the proper navigation, was to get precise calculation of the sinus function, of course, of cosine, which is just shifted a little bit, they find out that the angles they want to compute for proper navigation are only from area between 0 and p divided by 2. So if we are using this approximation as input, we use the values only from this input, we are getting very quickly, very efficiently, exact results. And my question is, can machine learning, can neural network come with a solution like this? We try to answer this question. And for this, we have to learn a little bit how simple neural network works. Neural network, as the name suggests, uses neurons, and this is really like parallel to the neurons we have in human brains. The neuron has usually inputs. On these inputs, we can imagine these inputs like features, like properties. Let's say we want to find out if I'm going to sell my flat in Manhattan. So as a feature, I can give flat size, numbers of rooms, numbers of toilets, and numbers of heliports, for example. Not every of these features had the same weight on the result. So for this, we are using weights. These are these W's values, which are kind of balancing the input value to the end result. We are doing the sum. Also, as a detail, we have this bias where we again can a little bit linearly correct the weights. On the end, we have activation function, which decide if we want to fire or not. It's like really like in the human brains, you are getting from the outside different inputs, but you are not reacting immediately. It depends on some value. And if the value reaches the activation, then neuron fires. As a most simple activation function is this rectifier linear unit, which just ignores the negative values, so we are not reacting on flats with zeros, number of rooms, and so on. So we react only on non-zero values. This is the simplest one. The neurons alone cannot do much work. So usually we are organizing the neurons together. In machine learning, we are organizing into the layers. In the human brain, it's more complicated. They are connected all together, everybody. So we have layers, and in case that every neuron in every layer is connected to each other, we call this network as a dance. Again, so we have, as blue, we have input values, which are connected to the yellow neurons which are as hidden. We cannot see them from the outside. And as a result, we are getting value on the beginning, on the outside. And if we are getting value, we are doing simple calculations. So we are calculating the weights from the particular inputs and putting into the neurons. It's the same we are doing for the second one and the first last one. And as a result, we can see that this multiplication can be added as a matrices. So the same happens to here. We are multiplicating the first row with the first column, second column, and so on. As a result, we can get this simple implementation in Kotlin. So again, we are iterating over layers. Every layers are multiplicating data with the weights. Weights are added biases are added to the weights. And on this result, we are just firing the activation function. Data weighted biases variable are matrices or even tensors. Depends on how big your network is. But having this nice writing in the Kotlin, it's very, very good readable, and you can see what's going on. I've mentioned already multiple times that we have a process called the training. So where is this training coming from? What does it mean the network is trained? For now, what we have seen was the forward propagation, where our values from the input are through the weights going through the layers on the outside. And the training begins on the end, on the output of this, where we are trying to find out how our output is similar to the expected value. On the beginning, our weights are either random or zero, so for sure, in the first step, we are going to get error. And in order to find how big the error is, we are using so-called loss function. I'm showing a mean square error as a most simple one. We have a backpropagation process where exactly this training happens. So according to this loss function, we are trying to find new values for our weights and for our biases that in the next step we are getting the smaller error. And in principle, it's just optimization function when we are trying to find optimum for the values where our loss function is to have a minimal value. And here our good friend for the beginning, the gradient descent, is coming in. Of course, for the simple systems, you can calculate this analytically, but it doesn't work in real world when your matrices are huge. Even small image, like 28 times 28 pixels, is already about 700 bytes. So, and for this, you have to do matrices in inversions, and these are really compute intensive. So we are not using analytical solution for that. We are using, with the gradient distance on similar algorithm, optimization solution. So we are trying, going to back, to find values for our weights, so that when we run the forward propagation again, our lost error will be slow as possible. Of course, we are not getting this to zero. And this process is called training, and we are doing this training in the FX. This is a sample in the Kotlin, written with the machine learning framework called Kotlin DL. It's coming from JetBrains. And this is one of implementation with two layers, with 4 layers, input, and two hidden layers, and the fourth is the output layer, which made after, I guess, about 1,000 epochs, was able to find out the values for the weights, getting the similar results as the optional, most simple function is providing. So it looks like a lot of work just to get calculated sinus, right? And it is. So if you are thinking about starting with machine learning, learning about data science to improve your developer life, you will find out that there's a lot of things. I guess I've scared a lot of you with mathematics, and I hope that at least what I've tried to do to show the beauty of the mathematics. Maybe not everybody was liking mathematics in school, so I didn't. But now if I learned about from the practical usage, how we can apply math in the real world, somehow it's became beautiful for me. So the topic learning how to learn became very interesting if I started to work in this area. And there are a lot of new findings, a lot of new knowledge in the area of neural science, how a human brain is working, that it makes sense to have a look on that and maybe trying again to find out what kind of learner I am. Do I learn better if I see the visual, I learn better if I hear stuff? And there's also different ways of learning modes. So just a little bit pimping on your brain, you can better learn. Healthy lifestyle is also part of this, because we know, meanwhile, that even new neurons, new neuron connections can be created, even if you are older, if you are living healthy. What is also very useful, and it is really cool, especially in machine learning world, that you have access to the huge amount of information and sources on the Coursera, on all of these massive open online courses. On the YouTube, we will find recordings from Stanford, MITs, which are leading pioneers in respective areas for the people who even invented the stuff we are already using. And we will probably also find courses with the Andrea Karpati there. And the best thing when, I guess it's everybody doing already, is learning by doing. So if you want to learn how, for example, this forward propagation or backward propagation works, maybe it makes sense just to start up and try it by yourself. I want to also to talk how is data science related to your Android developer life. This is the first conference for after a long time where I don't have to explain people why Android love Kotlin. And I'm really happy about that. And also data science is kind of big with Kotlin. JetBrains had a great commitment on data science. If you go on their homepage, you will very quickly find a dedicated area with libraries, tools, articles, and even JetBrains, they have a department called JetBrains Research, where also not JetBrains employees are contributing on the scientific research and implementations. KScript is very useful, even not for data science, if you want to do something quickly. And there are two well-known libraries coming from math, called KMath and Kotlin Grid. The second one is used for calculating differentiation. And Krangle and Plotly are more known from the area of data processing. So for example, if you are creating some logs and you want to get some simple evaluation on them, how many crashes you had, you don't have to write a program for that with Gradle and so on. You can do it very quickly with the KScript and these two libraries. Kotlin DL, I've already mentioned. It's early stages. It's even using older library of TensorFlow, but it's working fine. As the Android and JVM developer, you have access to all data science and machine learning libraries being available in JVM. So we didn't start with Android first. We already have, there is a lot of libraries, a lot of connectors if you are doing data science, like Spark and so on. You will for sure, if not in Kotlin, you would for sure will find the libraries in Java. Another very interesting use case for Android is the learning on the edge case, on the edge. What does it mean? Probably you heard about issues with Apple and scanning images on their phone, and we are coming to the era where people start to like their privacy. And if you want to have some interesting use case using machine learning, and you don't want to send this data to the cloud to do it on the big machines, you want to do it locally on the phone. And this is something what I expect soon became a part of normal mobile phone application, where you, as a mobile developers, are requested to contribute and to implement some stuff in your apps. For that, we have different machine learning frameworks which are already ready. And Google, I have to say that, had made a really great work with the TensorFlow framework, especially with TensorFlow Lite, which you can use very quickly in your application. They are providing the web page or portal called TensorFlow Hub, where you can already find a lot of pre-trained models. So you can very quickly write a simple application where you are grabbing a picture from your camera, and you can use already trained model by big guys on big machines to find out that on picture there is a cat. I know it was quite a quick, and I will show you another very nice use case, how we can use Kotlin for machine learning and data science. So let's see if I'll make it to switch to the demo. And for that, I am not going to switch to IntelliJ. I will stay in browser. or not? And what I'm opening is called a Jupyter Lab. I hope I can see that. And then what I'm going to show you is the code, what I have written to paint the pictures used previously in the presentation for showing the sign and approximate the sinus function. So this is a completely Kotlin code. You are working in the interactive mode in the cells. So it means if you write any valid Kotlin code, like it will be executed as a script, and if I give up the value, I will get the value. The Kotlin Jupyter kernel, it's written by JetBrains. It's really well supported. Is in development, so all the new features are coming, are put it in. And for example, what we are already getting is like data context-sensitive help and so on. So we can write, okay, what I can do on the variable A. So it knows that it's an integer, so maybe it's tell me that I can convert it to car and so on. So this is working really well, and maybe we can have a look on the very beginning. So I am creating the values for the x-axis. I am creating a sinus by mapping to the epsilon, and then I'm using simply plot from the library Plotly, which I bind in on the beginning, just to render them as the curve. So it was to the demo, and I continue back to the presentation. I can see my mouse here. No. Oh. So all the time we was dealing with the question, are computers, are software algorithms capable to write a better code as we do? I don't know. You have to find out the answer for yourself. I believe that there is a lot of chance that we will get very useful helper in the future. There is a chance that we will end up like this battery cell. I don't know. So it's up to you how you are going to use these powerful tools, how you're going to implement this into your application. Thank you very much. Maybe we have. Thank you.